All right, in this video, we're going to talk about section 3.6 dealing with related rates. And in this video, we're going to be evaluating related rates when X and Y are functions of time, and we're going to be solving applications involving related rates. All right, now related rate problems involve three variables here. You have an independent variable, which is often going to be T for time, and your two dependent variables. Now, the objective here, when you're doing related rates, you're going to find a formula for the rate of change of one of the independent variables in terms of the rate of change of the other one. And these problems are solved by using a relationship between variables, differentiating it, and solving for the term you want. So what I have here on the first page of your handout is a procedure for solving related rate problems. Number one, what you want to do here is read the problem carefully, making a sketch to organize the given information. Identify the rates that are given and the rate that is to be determined. Then step number two, you're going to write one or more equations that express the basic relationships among the variables. And then next, you're going to introduce rates of change by differentiating the appropriate equation or equations with respect to time. That's very important, okay? Each variable will be differentiated with respect to time. That's why it's called a related rate. Related rates here in this case. And then number four, you're going to substitute known values and solve for the desired quantity. And then step number five, you want to check that the units are consistent and the answer is reasonable. Like, does it have the correct sign? Okay, so you do want to check to see that your answer is reasonable. And sometimes you want to make sure that sign is correct here, whether it has to have a positive sign or a negative sign. All right, so now we're going to apply this procedure to some examples that I have here in this video, starting with this first one. We want to assume that X is equal to X of T and Y is equal to Y of T. And we want to let Y is equal to X cubed plus 3. And here, dx dt will be equal to 5 and X is equal to 4. Okay. Now, we want to find out what dy dt is when X is equal to 4. Okay. So here we're given what dx dt is. That's 5 when X is equal to 4. So we're going to find dy dt when X is equal to 4. So here's our equation that's given to us. Y is equal to X cubed plus 3. All right, in this case here, we want to differentiate each variable in this equation with respect to time. So in other words, the derivative of y, now when I differentiate y, I'm going to have the derivative of y, which will be 1, but it's going to be with respect to time, so it'll be dy dt. And that's equal to the derivative of x cubed. That would be 3x squared. Now, since I'm differentiating with respect to time, I have to include dx dt. Here I'm differentiating the y with respect to time and the x with respect to time. So that's why you see dy dt and dx dt. The derivative of a constant is 0. So this is what I have. 1 times dy dt is going to be dy dt. And that's equal to 3x squared times dx dt. Now I can find out what dy dt is going to be when x is equal to 4. And we're also given that dx dt is going to be equal to 5. So we just substitute here. So it'll be 3 times the x, which is 4. So it'll be 3 times 4 squared times dx dt. That's given to be 5. Okay. So in this case here, this will be 3 times 4, and I can hit the x squared button to square it, times 5. So in this case here, dy dt, when x is equal to 4, ends up being 240. That's all we had to do in that problem right there. So here we have to differentiate the x and the y with respect to time. Here's another example. Assume x and y are functions of t. I'm going to evaluate dy dt for 3xy minus 4x plus 2y cubed equal negative 16, with the conditions that dx dt is equal to negative 4, x is equal to 2, and y is equal to negative 1. And I will go ahead and rewrite that equation. 3xy minus 4x plus 2y cubed equal negative 16. Here we're going to differentiate each and every term in this equation with respect to time. Now for the 3xy, I have to use the product rule because I have 3x times y. So using the product rule, I'm going to do this. The first term is your 3x times the derivative of y with respect to time. So if I take the derivative of y, that's going to be 1, but that's going to be multiplied by dy dt. And then plus the second, which is y, times the derivative of 3x. That's just going to be 3, but I need to include dx dt because x is being differentiated with respect to time as well, just like y is being differentiated with respect to time. And then minus the derivative of 4x would just be 4, and I need to include dx dt. Plus the derivative of 2y cubed. Bring this exponent down, multiply by 2, you'll get 6. Copy the y down to the 1 less power, it'd be y squared. But again, it's being differentiated with respect to time, so I need dy dt. Equal the derivative of a constant, negative 16, that's 0. All right, now let's clean this up just a little bit. I'm going to bring down the 3x dy dt plus, put the 3 in front of the y, that'll be 3y dx dt minus 4 dx dt plus 6y squared dy dt. That's equal to 0. So here we're going to evaluate dy dt. That's what we're trying to find. We're given that dx dt is negative 4, x is equal to 2, and y is equal to negative 1. So let's substitute those values into this line right here. So it'll be 3 times x, which is 2. So I got 3 times 2 times dy dt, which is what I'm trying to find, plus 3 times the y, which is negative 1, times dx dt, that's going to be negative 4, minus 4 times dx dt, again, that's negative 4, plus 6y, well, y is negative 1, and that negative 1 is going to be squared. dy dt is what I'm trying to find. And that's equal to 0. So I'm just substituting dx dt with negative 4, x with 2, and y with negative 1. Simplify this. 3 times 2, that will be 6. So I have 6 times dy dt. Let's see, negative 1 times a negative 4 will be positive. 4 times the 3 in front would be plus 12. Minus 4 times that negative 4 would be plus 16. Then if I square this negative 1, that's going to be positive 1 times the plus 6. That would be plus 6 times dy dt equal 0. Now, if I combine like terms on the left side, 6 dy dt plus another 6 dy dt, that's going to be 12 times dy dt. And then 12 plus 6 will be 28, so that'd be plus 28 equal to 0. Now I can solve for dy dt by first subtracting 28 on both sides. So that means I'm going to have 12 dy dt equals negative 28. And then to get dy dt by itself, you'll divide both sides by 12. So that means dy dt is equal to negative 28 twelfths. But I can reduce 28 twelfths by dividing the numerator and the denominator by 4. So that means dy dt ends up being negative 7 thirds. Because 4 goes into 28 7 times, 4 goes into 12 3 times. So dy dt ends up being negative 7 thirds. Okay. All right, let's look at this next example right here. A point is moving on the graph of x times y equal 20. When the point is at 5, 4, its x-coordinate is increasing by 5 units per second. How fast is the y-coordinate changing at that moment? Okay. So we're told that the x-coordinate is changing at 5 units per second. So in this case, dx dt, that's a change in x with respect to time, is going to be 5. And here we got the 0.54. That means x is going to be 5 and y is going to be 4. So we want to find out how fast is the y-coordinate changing at that moment. That's a derivative of y with respect to time, dy dt. And here's our equation, the graph xy equals 20. Now we're going to differentiate this implicitly, well, with respect to time. X times y, that's a product. We need to use the product rule if we're going to differentiate this with respect to time. So using the product rule, the first term is your x times the derivative of the second, the derivative of y will be 1, but it's going to be dy dt since we're differentiating with respect to time, plus the second, which is your y, times the derivative of x, that's going to be dx dt. X is also being differentiated with respect to time. And that's equal to the derivative of 20. Of course, that's going to be 0. All right, now let's do some substitution here. In this case, I'm going to go ahead and write this out as x is equal to 5 and y is equal to 4. So x is 5, so that will be 5 times dy dt is what we're trying to find. Plus the y, which is 4, times dx dt, that's going to be 5. So if I simplify this, this will be 5 dy dt plus 20 is equal to 0. If I subtract 20 on both sides, I'm going to have negative 5 dy dt. Not negative 5, it'll be positive 5 when I get the negative 5. All right, 5 dy dt is equal to negative 20. Okay, now rewrite this. That way you'll be able to see that I'm going to divide both sides by 5 to get dy dt by itself. So dy dt ends up being negative 4. Okay. And since dy dt is negative, that tells me that the y-coordinate will be decreasing. So the y-coordinate is decreasing at 4 units per second. So that's how we solve that particular related rates problem. All right, take a look at this example, number 4. Here's some type of application problem with this one. A boat is being pulled toward a dock as shown in the figure to the right. If the rope is being pulled in at the rate of 2 feet per second, how fast is the distance between the dock and the boat decreasing when it is 3 feet from the dock? All right, now let's take a look at this problem and how this is illustrated in this picture. Notice we have a right triangle. We've got a right triangle in this case here. So that means we're going to need to use something called the Pythagorean theorem. And I don't know if you remember this, but the Pythagorean theorem is this. We have a squared plus b squared equaling to c squared. In other words, the longest side is the hypotenuse here, which is your rope. The square of that hypotenuse will be equal to the sum of the squares of the other 2 legs in that right triangle. So this could be A, and this could be B, which is your 5 feet. Okay, now we're trying to find out how fast is the distance between the dock and the boat when it is 3 feet from the dock. So that means it is coming inward. This boat is coming inward this way. So this length here will be decreasing. All right, now keep in mind the this right here, the distance from the dock up to where the rope is being held, that's going to remain the same. Okay, and also we're told here, if the rope is being pulled at a rate of 2 feet per second, this rope right here is being pulled at a rate of 2 feet per second. So that means dc dt that's going to be 2. And also in this case here, we're told something else. We're also told here when, the rope, or how fast is the distance between the dock and the boat decreasing when it is 3 feet from the dock. That means when the boat is 3 feet, that's going to be your A, which is equal to 3. Okay, so we know what A is, and we know what B is. That's 5 feet. Let's find out what C is using that Pythagorean theorem. A squared plus B squared is equal to C squared. So if we substitute our A with 3, we're going to have 3 squared plus substitute the B with 5 feet. That's 5 squared is equal to C squared. That's going to be the length of this rope. 3 squared is 9, and 5 squared is 25. So we got 9 plus 25 is equal to C squared. 9 plus 25 will be 34, so 34 will be equal to C squared. And then to find out what C is, the opposite of squaring something would be to take the square root. On both sides. And in this case, don't worry about the plus or minus symbol, because length can't be negative. So the square root of C squared will be C, and I'm going to leave this as the square root of 34, since 34 is not a perfect square. Okay. Since B is going to be 25, the formula that we're going to be using here is this. We're going to use A squared plus B, which is 5, and that's going to be squared, is equal to C squared. That's the equation that we're going to be using here. And then 5 squared will be 25. So A squared plus 25 would be equal to C squared. It's this equation that we're going to use implicit differentiation. We're going to differentiate with respect to time. Okay. It's this right here we're going to differentiate with respect to time because they're asking how fast is the distance between the dock and the boat. That means we're trying to find what dA dt is going to be. How fast. So dA dt is what we're trying to find. Now let's differentiate this with respect to time. The derivative of A is 2a, but we need to include dA dt. Plus the derivative of 25, that's 0. That's equal to the derivative of c squared would be 2c times dc dt. Now let's do some substitution here. We let A be 3. So that's 2 times A, which is 3, times dA dt is what we're trying to find. And that's equal to 2 times C. We found this out to be the square root of 34 times dC dt. That's given to be 2. Because it is told that the rope is being pulled at a rate of 2 feet per second. So that means this distance is being pulled. So dC dt is 2 feet per second. If I simplify this, 2 times 3 will be 6. So this will be 6 dA dt is equal to 2 times 2, which is 4 square root of 34. And to find out what dA dt is, we're going to divide both sides by 6. So dA dt is equal to 4 square roots of 34 divided by 6. Use my calculator and clear this out. 4 second x squared for the square root of 34. Now get out of that. We'll find out what that is and then divide by 6. To 3 decimal places, this will be approximately 3.887. So dA dt will be 3.887, and this will be in feet per second. So to answer that question here, the speed that the distance between the dock and the boat decreasing when it is 3 feet from the dock. That distance is decreasing at 3.887 feet per second. Okay, next example deals with the radius of a spherical balloon is increasing at a rate of 0.7 centimeters per minute. How fast is the volume changing when the radius is 7.9 centimeters? Okay, so this is something you need to know. We're dealing with a spherical balloon. There is a formula for finding the volume of a sphere. And that's going to be this. V is equal to 4/3 pi times the radius cube. Now, we are told in this problem that the radius is increasing at a rate of 0.7 centimeters per minute. So that would be dr dt, which is 0.7. And here the radius is going to be 7.9 centimeters. So r is 7.9. And we want to find out how fast is the volume changing. So the dv dt is what we're looking for in this particular situation, dv dt. Okay, so since our volume formula is this, let's find out let's differentiate this with respect to time. So the derivative of v will be dv dt. 4/3 and pi are going to be constant. So I'm going to bring down the 4/3 pi. The derivative of r cubed with respect to time, that's going to be 3r squared times dr dt. Keep in mind, all the variables are going to be differentiated with respect to time when we're dealing with related rates. All right. dv dt is what we're looking for. And that's going to equal to 4/3 pi. And the radius is 7.9. So v times, actually, if I simplify this a bit, let's just simplify this just a bit. Because I got 3/1 times 4/3. Those threes divide out. So I can write that as 4 pi times the radius, in this case, is 7.9. And that's squared. And times dr dt will be 0.7. Okay, so let's see here. 4 times on this calculator, if I do second and hat for the pi times 7.9 and then square it times 0.7. Let's say I want to round this up to the nearest whole number. This will be approximately 549 centimeters per minute. 549 centimeters per minute. Okay. Okay. So that represents the speed of the volume changing when the radius is 7.9 centimeters. So that means your volume is going to be changing at 549 centimeters per minute. Okay. All right, here's another example, another application problem. Excuse me. A 17-foot ladder is placed against a vertical wall. Suppose the bottom of the ladder slides away from the wall at a constant rate of 3 feet per second. How fast is the top of the ladder sliding down the wall? And it's going to be a negative rate when the bottom is 15 feet from the wall. Okay, so let's draw a figure so that way you can get a visual idea of how to solve this problem. Sometimes drawing pictures does help. Let's say this is the ground right here. Here's a vertical wall coming this way. This right here is the wall. And then you got that 17-foot ladder placed against this vertical wall. So this right here, and keep in mind my drawing's not that great. This right here represents a ladder. and it's placed against a vertical wall. And here the bottom, which is right here, is going to be sliding away from that wall at a constant rate of 3 feet per second. So here is going in this direction, sliding away at 3 feet per second. And by the way, we can just label that the ladder, that's going to be 17. And if you look at this, this is in the form of a right triangle. Okay, so I'm going to draw a little bitty box here to indicate that this is a right triangle. And of course, the ladder is 17 feet, as you can see. Now, this is going at a rate of 3 feet per second. Now, we want to find out how fast is the top of this ladder sliding down this vertical wall, because it's going to be coming down this way. When the bottom is 15 feet from the wall. Here's the bottom part. We're going to say that it's 15 feet away. So in this case, we can use the Pythagorean theorem since we're dealing with a right triangle. A is 15. B is what we're trying to find. C is 17 feet. Okay. Now notice that the length of this ladder is not going to change. These two legs right here will be changing. From the vertical wall, that's changing. And then from the bottom of the ladder to the distance from the wall to the bottom of the ladder will be changing as well. All right, so we're also told ladder sliding away at a constant rate of 3 feet per second. So that means dA dt is 3 feet per second. All right, so now if you recall the Pythagorean theorem, is this: a squared plus b squared is equal to c squared. That's the length of the square of the hypotenuse is going to be equal to the sum of the squares of the lengths of the two other sides in that right triangle. So A is going to be 15. B is what we're trying to find. We know what C is. Okay. So let's substitute the A with 15. So it'll be 15 squared plus B is what we're trying to find. B squared is equal to 17C. I mean squared. That's what C is, 17. Square the 15, that'd be 15 times 15, or 225. Plus B squared is what we're trying to find. 17 squared is 17 times 17, or 289. And then to get B squared by itself, we subtract 225 on both sides. So that means B squared is equal to 64. And then to find out what B is, we take the square root on both sides. And we're going to be using a positive value because lengths are not going to be negative. And of course, square root of 64 would be 8. So that means your B is going to be equal to 8. All right. Now I'm going to rewrite again that Pythagorean theorem formula: a squared plus b squared is equal to c squared. Now notice that A is changing at a rate. B is going to be changing at a rate because we're going to find out how fast is the top of the ladder sliding down this wall. That's what we're trying to find. The length of the ladder will never change. So I'll just go ahead and substitute that C with 17 because that's our hypotenuse in this case. So I have A squared plus B squared is equal to 17 squared, which is of course 289. Now we're going to differentiate this with respect to time. So the derivative of A squared will be 2A, and that's multiplied by dA dt, plus the derivative of B squared, which is 2B. And then that will be dB dt. It's equal to 289. So in other words, we're looking for dB dt. We want to know what that is. Now let's do some substitution here. 2 times your A, which is 15, times dA dt, that's given to be 3, plus 2 times the B is 8, times dB dt is what we're trying to find. And I think I made a mistake here. If you take the derivative of 289, that needs to be 0. Because the derivative of a constant is 0. Because I'm differentiating each side of the equation with respect to time. So that would be equal to 0. Let's see, simplify this. 2 times 15 is 30 times 3, which is 90. So I have 90 plus 2 times 8, that's 16 times dB dt is equal to 0. And to get dB dt by itself, I need to subtract 90 on both sides. So that means 16 dB dt equals negative 90. Then divide both sides by 16. So dB dt, we know that's going to be negative. And that is to be expected because the ladder will be sliding down the wall. So negative 90 divided by 16 would be negative 5.625. And this is in feet per second. Okay. So in this case here, I might need to bring this down a bit. Okay. In this case here, this wall, the ladder will be sliding down this wall at a rate of negative 5.625 feet per second. Okay. All right, here's the next example. All right, in this case here, suppose that for a company manufacturing calculators, the cost, revenue, and profit equations are given by C of X is equal to 70,000 plus 40X, R of X is equal to 200X minus X squared divided by 20, and P is equal to R minus C, where the production output in 1 week is X calculators. If production is increasing at a rate of 400 calculators per week, when production output is 6,000 calculators, find the rate of increase or decrease in cost, revenue, and profit. Okay, so here we're going to find the rate of increase or decrease in cost first. This is part A in that problem. And you're told what the cost function is. C is equal to 70,000 plus 40X. Okay. All right, so this is, of course, with respect to time. So again, we're going to be using related rates because you're talking about the output in 1 week. That's time. So we're going to be taking the derivative with respect to time of the left side and the derivative with respect to time of the right side. So the derivative of cost with respect to time, or the derivative of C with respect to time, would just be dC dt, equaling the derivative of 70,000, the derivative of a constant is 0. The derivative with respect to time of 40x, well, the derivative of 40x would just be 40, but then we have to tack on dx dt. because that X has to be differentiated with respect to time. Now you're told that the production is increasing at a rate of 400 calculators per week. So in this case here, dx dt is 400. And the production output is 6,000 calculators. So X is 6,000. So let's substitute dx dt with that 400. So dc dt is equal to 40 times 4,000, which equals 16,000. So to answer the question here, since it's a positive number, costs are, and it will have you choose either increasing or decreasing. So since it's positive, it's going to be increasing at a rate of $16,000 per week at that production level. So that's part A. Now on to part B. Here we're going to find the revenue, whether it's increasing or decreasing at a rate of how many dollars per week at this production level. Well, your revenue function was this. R is equal to 200x minus x squared over 20. Okay. So here we're going to take the derivative with respect to time of R on the left side and the derivative with respect to time on the right side. For 200x minus, I'm going to write this as 1 over 20 x squared. So the derivative of R with respect to time would just be dr dt. That's equal to the derivative with respect to time of 200x will be just 200, but we must include dx dt, as x is being differentiated with respect to time, minus 1/20 times x squared. If I bring the 2 down, this will be 2 over 20. But you have to understand that 2 over 20 will be 1/10 if I reduce it. Copy the x down to the 1 less power, and that's going to be dx dt as well. Let me put 1/10 x in parentheses. Now let's do some substitution here. Dx dt is 400 and x is 6,000. So that means dr dt that's going to be 200 times dx dt, that's 400, minus 1/10 times x, which is 6,000, times dx dt, that's 400. Okay. Let's do this here. 200 times 400, that would be 8 with 4 zeros. That's going to be 80,000 minus 1/10. If I do in parentheses 1 divided by 10, close parentheses, times 6,000 times 400. That'd be 240,000. Now I know this is going to end up being negative, so 80,000 minus 240,000 would be negative 160,000. So what that means here is that the revenue is either increasing or decreasing. Since it's negative, that means our revenue is decreasing. I'll write the word decreasing here. at a rate of, and I'll write the 160,000 without the negative because I'm indicating that revenue is decreasing at a rate of $160,000 per week at the production level. Okay. So that's what that negative 160,000 means. Okay, and then part C is this. Profits are increasing or decreasing at the rate of how much per week at this production level. If you recall, when you find a profit, that means revenue minus cost. And if I take the derivative with respect to time of the left side and the right side, here's what I have. The derivative of the profit would be dp dt, and that's with respect to time. That's going to be the derivative of the revenue minus the derivative of the cost, both with respect to time. So it'll be dr dt minus dc dt. Well, the revenue, the derivative of the revenue with respect to time, we found that out in part B to be a negative 160,000 minus the cost, which was 16,000. We found that out in part A. So negative 160,000 minus 16,000 will be negative 176,000. Okay. So to answer part C, the profits are, in this case, decreasing. At a rate of $176,000 per week at this production level. Okay. And I'm going to bring this back down here so that way you can see how I worked each one of those out. In part A, I found the cost to be $16,000. It's increasing at that amount per week. Then the revenue in part B was decreasing at $160,000 per week. That's where the negative sign comes in. And then, of course, I just took the derivative of the profit minus the derivative of the revenue minus the derivative of the cost, all three with respect to time. It's decreasing at negative $176,000 per week, decreasing at that amount. And finally, number 8. Last example in this video. A tanker that ran aground is leaking oil that forms a circular slick about 0.1 foot thick. To estimate the rate, which is dV/dt in cubic feet per minute, at which oil is leaking from the tanker, it was found that the radius of the slick was increasing at 0.43 foot per minute. That's dr dt, equaling to 0.43, when the radius, capital R, was 500 feet. Find dV/dt using pi equaling to approximately equaling to 3.14. So here's the illustration of that. And they do give you the formula. A is equal to pi times the radius squared. And they tell you that V is going to be equal to 0.1 times A. Okay, so let's identify what we have here. The V is equal to 0.1 times A. Now, of course, it is a circle, by the way. So that means your area of the circle is going to be pi r squared. That's given to you. So we just substitute that A with pi r squared. And you're told that the radius, which is capital R, that's 500 feet. You're also told it was found that the radius of the slick was increasing at the rate of 0.43 foot per minute. That's dr dt. And they even say that right here. And we're told to use pi to be approximately 3.14. And we're trying to find dV dt. So that's pretty much straightforward right there. They're telling you, they're giving you these values here. They're giving you dV dt and dr dt. So all we need to do is find out what dV dt, the change in the volume with respect to time. All right, let's differentiate this equation with respect to time. Differentiate the left side and differentiate the right side with respect to time. All right, the derivative of the volume with respect to time would just be dV dt. That's equal to 0.1 in pi or constant, so I'll just bring those over. The derivative of r squared with respect to time would be 2r and then dr dt. Bring the 2 down, copy the capital R with the 1 less to the 1 less power, and r has to be differentiated with respect to time, so that's where dr dt comes in. Okay, so now the next thing I need to do is just do some substitution, if this helps. Well, before I do that, if I do 2 times 0.1, that would be 0.2 times pi times r dr dt. Now let's do some substitution here to find out what dV dt is. All right, 0.2. Pi is approximately 3.14, so we're using that. Times r, that's the 500. Times dr dt, that's 0.43. So if I do dV dt, multiply all this out, this will be 0.2 times 3.14 times 500 times 0.43. And if I round that off to the nearest whole number, it would be approximately 135 cubic feet per minute. Volume is in cubic feet, so it'd be 135 cubic feet per minute. So in other words, the volume will be increasing at a rate of 135 cubic feet per minute. Okay, and that's all there is to that problem. All right, so that concludes this video on section 3.6 dealing with related rates. Feel free to reach out to me if you have any questions about any of the problems that were presented in this video or any of the homework problems on this section in my math lab.